Chapter 17 is on applications of constrained least squares. Each of the applications in itself is like a huge field. You can take whole courses, multiple courses on them. But it's just to show you it's a very, very simple introduction, and you can actually do something with constrained least squares. So our first one is going to be on portfolio optimization in finance. Okay, so here's the setting is that we're going to invest a total of V dollars. V is positive in n different assets. These could be different stocks, bonds, ETFs. I mean, it actually doesn't matter what they are over some period. Could be a day, week, month. I mean, this doesn't matter. Now, our investments can include short positions. Now, a short position is essentially owning a negative amount of something. And what it means is you borrow the asset, for example, a share of Google stock. I borrow it, sell it immediately, so I receive cash. But now I have the obligation to repay or to pay back to return one share of Google later at some point. So that's the idea. And it turns out that's pretty much equivalent to owning a negative share of Google. At first it sounds strange, and it is strange, but that's what it is. Okay. Now, we can describe our portfolio by a portfolio allocation weight vector W, okay? And this is relatively common notation. And what it does is Wi, or Wj, gives you the fraction of your total portfolio value that you hold in asset J. And that means, for example, that capital V, that's your total portfolio value in dollars, times Wj, that gives you the dollar value of how much you hold of asset J. Okay, now, well, by construction, W1 transpose W, which is the sum of the weights, is 1. And that's why it's supposed to be a weight vector, right? It's something that adds up to 1. Now, they're not necessarily non-negative, the entries. They could be negative. And when you see a negative 1, that simply means a short position. In fact, the term for a portfolio that doesn't contain negative weights or short positions is long only, because you can have a short position and a long position. Long position means you actually own the thing. And so a long only portfolio is one where the W, all the entries in W are non-negative. Okay, so here's a very specific example with 3 assets. I have my weight vectors minus 0.2, 0.0, 1.2. Notice that the weights do sum up to 1. Okay, and what does this mean? Well, it means that we actually take a short position of 0.2 capital V, that's in dollars, in asset 1. We don't hold any of asset 2, that's what the 0 means here. And then in asset 3, we hold 1.2 times our value. So roughly speaking, what happened is we sold asset 1 that we don't even have, used the proceeds to buy more of asset 3 than, well, even than the total value of our portfolio, right? So that's kind of the idea. Now, obviously, you would only have a portfolio like that if you thought for some reason, the first asset was going to go down in value and the third asset was going to go up. And the reason is pretty simple there, that if the first asset goes down in value, then later when I make good on my obligation to return the short position, or close out the short position is how people would say it, it's cheaper for me. So I've made money on that. And if the third asset goes up, then when I sell it, I'm going to do well. So anyway, that's the basic idea. Okay, so there's a concept of leverage. Actually, there's several different definitions of leverage. And as far as I can tell, all are used. So, and it's no big deal. You just have to ask somebody when they say the leverage is 2, what they mean. Which definition are they using? So here's the definition we'll use because it's simple. It's the sum of the absolute values of the weights. Okay, so that's the idea. Another definition that's quite common is our L minus 1 and then divided by 2. So and I think both are used. Now, I'll henceforth use our definition of leverage. So capital L, the leverage is 1 when all the weights are non-negative, because when the weights are non-negative, the absolute values up here are actually equal to the W. You don't need the absolute values because they're all non-negative. And then L is the sum of the W's, but that's 1. So, and that's the smallest the leverage could be. So that's a long only portfolio. This tells you the leverage is 1. Some people would say you are unleveraged, right? So leverage generally means if it's bigger than 1, it means at least one of the weights is less than 0. It means you hold a short position. And by leverage, what it means is you've sold some assets, whichever ones you're holding short, and use the proceeds to pile more money into other investments. That's kind of the idea behind leveraging. Okay. Another portfolio that comes up is the so-called 1 over n portfolio, or in our language, the 1s over n portfolio. And that's also called the uniform portfolio. And it's basically like, if you got 10 assets, put 10% of the total value in all of them. That's it. Okay. Now, another common assumption is that we'll often assume that asset n, some people use asset 1, doesn't matter, is risk-free, is the way people would say that. And that's another way to say that. People also say cash or treasury bills. The idea being is that there's not much risk in treasury bills. Okay, so that's like asset n is a special one. It's risk-free. Actually, it's kind of interesting. At some point, all these things start sounding the same. That's very much like in regression or something when I'm building a model. And my first basis function is the 1s vector, right? So my first basis function is the constant function 1. And so that one is special. It's a constant. And we'll see that that's kind of what this is as well. So with that assumption, if you have W equals En, it says put all of your 0 of your portfolio on assets 1 to n minus 1, and put 100% of your portfolio value on asset n. If asset n is cash, then you'd say, well, that's the portfolio is in all cash. Okay, so it's just some basics. Okay, now we'll talk about the return over a period. So what we'll do is we'll let R tilde sub j, it's going to be the return of asset j over the period. And we'll define that as the fractional increase in the price or value. And it's a decrease if it's negative, right? If the return is negative, it means it decreased in value. And it's often expressed as a percent, like, plus 1.1 or minus 2.3. So if you say the return was minus 2.3%, it means that, for every dollar you put in, the value at the end of the period was whatever it would be. So 97.7% cents. Okay, so that's what that means. Now your portfolio value also changes over the investment period, and we're going to call the after investment period value of your portfolio V plus, and the initial portfolio as V. So V plus minus V is the increase in value of your portfolio. Now it could be negative, right, which means you lost money, or lost value. But that's what it is. It's simply the increase, and I'm not saying it necessarily increases, but it's the increase in the value of the portfolio, and I divide that by the initial value, and then that is the fractional increase in the value of the portfolio. That's called the portfolio return. And it turns out that is exactly simply R tilde transpose W, where R tilde is the fractional, is the return, the vector that gives you the fractional returns of all the assets. Right? So here you go. It's just, in other words, we're back to week 1 of the class. It's just an inner product. So if you have, the weights, taking the inner product of the weights with the fractional returns of the assets, individual assets, gives you the fractional increase in value or the return of the whole portfolio, just inner product. Okay. Now, what happens is if you hold a portfolio for T periods, and the returns over that periods are R1, R2, R3, and so on, then the value at the end of the period is this. It's actually, you take a product of, it's V1 times 1 plus R1 times 1 plus R2, and so on. So that's the actual value of the portfolio, right? So, and this is if I tell you, look, I put in $1 million and then it goes up 5% and then down 7, then up 3, then up 6, then down 2, that kind of thing, then the value at the end is going to look like that. So, because you're just each time you're just multiplying by 1 plus the return. Okay, and for some reason that's historical and that I don't know the origin of, portfolio values versus time are traditionally plotted using from an initial portfolio of $10,000. I don't know why, but it's a number maybe from the 60s or so. I have no idea what it is, but that's what it is. I mean, so you'll see that, but you'll see everything else. You'll see people start with $1 or something, and of course, it's linear in that amount, right? So if I double the amount you put in initially, then the total value at the end is double that. So okay. So in some sense, that doesn't matter. But just so you know, you're going to see things that are referenced to $10,000 at the beginning, and you might ask why, and the answer is, well, 2 things. Number 1, I don't know, and number 2, it's historical for sure. Okay. So this brings us to the return matrix. So suppose we're going to hold a portfolio with weights W over T periods. Okay, so this is the setting. And we're going to define an asset return matrix, which is going to be T by N. So here's T and N. I've drawn it as if it's tall. That's often the case, but not always, right? So we could easily have. I should say that the group of all the assets you're investing in, I'll teach you some slang, is called the investment universe. So N is the size of the universe of assets, and so it would be like here'd be the kind of things people would say, "What's your universe?" And the person would come back and say, I don't know, U.S. whatever, high cap, or who knows, that kind of thing. Anyway, there, now you know another slang word, okay? So, all right. So we make this return matrix R, and it's T by N. Now, the rows correspond to periods, time periods. And, a very common thing would be a day, right? But, I mean, none of this, the math works if this is every 1 minute, if it's every week, quarter, year, it really doesn't matter. But I'll continue speaking as if we're talking about daily stuff. Okay, so each row here is actually the transpose of the return vector over period t. So those are that's the row. So a row here would tell you how did all the assets do on that particular day. Okay, now a column is super interesting. A column focuses on a single asset, and it tells you the time series of its returns. Okay, so that's what that is. Now, the portfolio return time series is simply, well, it's matrix vector multiplication. You multiply this matrix by the weight vector W, and you get RW, and that's a time series. So little r is a time series, capital T long, of the portfolio return. So if you looked at it, it would be minus 0.01 plus 0.02 minus 0.005, and that means it kind of went down 1%, then went up 2%, then down 0.5%, that kind of thing. Okay, all right. So if the last asset is risk-free, which we're going to assume, then the last column that's the return series of that risk-free asset, and what that is, that's very simple. It is simply mu risk-free, which is a number, times ones. In other words, it's constant. So that's what it means to be risk-free. I mean, if you like, you can set mu risk-free equal to 1 or whatever. And then it just means it's like putting whatever dollars, under the mattress or something. It just, nothing happens. But what it really means is it goes up. And now, by the way, interest rates at the time, this is 2020, interest rates are like super low. So it might as well be 0, frankly. But in any case, that's the idea is that you get the interest rate on, if it's daily, 1 day's interest, so, which is extremely small right now, but it's fine. Okay, and that's called the risk-free per period interest rate. It makes perfect sense. I mean, if you scan, well, first of all, the standard deviation of that column is 0 because it's constant, and that's actually that's going to be one of our definitions of risk is, how much does the return vary? And that last column, it's 0, and that's why we call it risk-free. Now you look, if there's another column in there, which is Tesla or Google or something like that. Or you'll see it be positive, negative, positive. Who knows what it is, right? It's varying all around. And that's, of course, not risk-free. Okay, so so here I'm going to get a time series that's a vector, a portfolio returns. Now it depends on W, and we're going to go into great detail about that later. But for right now, we just say depends on W. It's W's fixed. It doesn't matter how you got it. Doesn't matter. But once you fix W, you get a time series of portfolio returns. That's R here. I could plot it. I could do all sorts of stuff. Now the average return, or people just say the return is the average of that. So that's the average return. And the risk is the standard deviation. So the standard deviation, the risk of your portfolio says how variable is the portfolio return. That's really bad. That's what the standard deviation measures. And so if it's 0, which would be the case if W equals EN, that means put the entire portfolio into the risk-free thing, then the risk is 0 because the return is mu risk-free. And the standard deviation is 0 because every single day you earn exactly mu risk-free. So that's what people call risk. Okay. Now they're related to the increase in value, not directly. It's not like it's equal to it, but here's the analysis. It says if you look at what is VT plus 1, that's what's the value of your portfolio. Basically, if you propagate forward T time steps from 1, right? Your initial time step. And it's equal to this. It's V1. And well, you remember, it's the initial value times, and then you just simply multiply by all the returns, right? Oh, by the way, some people refer to this process of taking the product of 1 plus things as compounding, right? So it means kind of if you do well, you reinvest, right? But for us, that's what the weight vector means. Now, I'm going to expand this now. And the first term I get is when I multiply all the ones together in this big product here. And that's going to give me V1. Then I get V1, and the next term is when I get in all of these, I take all of the ones, except one of them, and then I take one of the R's. And that's going to give me this term here. Now, what's missing, I can tell you what I have neglected in that approximation. I've neglected all the terms where there's products like, R3 times R7. And in fact, there's even bigger ones. The argument goes like this. If R is on the order of 1%, something, just roughly, right? If R is on the order of 1% or something, it's 0.01. And so this thing makes sense here. But when you multiply, two quantities on the order of 0.01, you get something that's 10 to the minus 4, and it's basically negligible. So, okay, so that's the approximation being made here, and that says that your value at if you go capital T periods in the future, it's basically your initial value plus your initial value times this number, which is T times the average return, right? So the basic idea is it tells you that the average return tells you something about the increase in portfolio value over that period. And look, if the returns are ridiculous things like plus minus 0.15, 0.2, then this is kind of a crappy approximation. But nevertheless, it's a good one for a lot of situations. It's actually a very good one. Oh, and the only thing I should say about that is this tells you why you would want the return to be large. I mean, it's kind of obvious why you'd want the return to be large. This quantifies it. It basically says it has to do with an approximation that tells you about your increase in value over some period. Okay. So usually both risk and return for a financial return time series are not quoted as per day or per week or per month or whatever you're doing. They're all converted to what it would be over a year, and that's called annualized. And that way it's easier, right? If I say what's the return on a thing, and you go, oh, not so bad, it's 15%. What they mean is it's 15% over a year. Now, what's the risk on it? That's also given as 12% over a year. Okay, something like that. All right. So the way you do that is the annualized return. That's an easy calculation. You simply multiply if there's P periods per year. then you simply multiply it. So if this is weekly, that might be 52, right? If it's daily, there's about, let's see, there's about 250, maybe closer to 252 trading days in a year. I mean, obviously, it depends on the market and all that kind of stuff. So it can be more, less. I mean, it can be all sorts of stuff. But a P would be about 250 there, is a good approximation of it, if it's daily trading. The annualized risk is interesting. You don't multiply by P. Actually, what you do is you take the standard the variance, and you multiply by P. Standard deviation is the square root of that, and so you actually have to take the square root of P. So it says that the annualized risk is the square root of P. So that's about 16 or something like that if you have 250. And it says if you had 250 trading days a year, your annualized return, right, would be 250 times the average of the daily return. And your annualized risk would be square root 250. And you know what? If it's not 250, it's 252 or 251. Go ahead and fix. This is just to give you a rough idea of what it is. Okay, so this is just I'm just saying if you go and read a book on finance or something like that, this is what you're going to see, and it kind of makes sense, right? Because otherwise, it's hard to in your head. People are going to do this calculation in their head anyway. So this is how people quote things. Okay, we now come. That's all the preliminaries, and we now come to the main question here, which is how should we choose the weights? Should we just make it uniform? That's the 1 over n portfolio, or written in math, it's W equals 1s over n. What should be W, right? Now, we have two desiderata. So there's two things that we want here. The first is we want high mean portfolio return, and we want low portfolio risk. So this is a bi-objective problem. I mean, immediately we can see that. It's a problem involving we want the mean to be high and we want the risk to be low. Now, the tricky part, I'm sure someone has said this. The tricky part is, of course, you don't know what the returns are going to be in the future. By the way, if you did, you don't need any of this to do very well. So yeah, if you had the possibility of knowing future returns, you could do very well without this. Okay, so we don't know that, but here's what we do know. We know, let's say, for example, last year's returns, because it's historical record. We can go look it up. So of course we don't know next year's returns, right? I should add, that's basically what happens if you walk into a hedge fund. That's basically what people are doing, is they're trying to figure out what are next year's returns. Not just hedge funds. I mean, any kind of people, anyone putting together a portfolio is basically doing that. They're trying to figure out, what's going to happen to Tesla. Might be in the next hour, might be in the tomorrow or 10 days from now, and it might be, quarter by quarter. Okay. So we don't know the future basically, but we do know the past. And so here's the idea, and it's this. We're going to choose a weight vector that would have worked well on past returns. That's what we're going to do. and this is a matter of faith, which is not always well-founded or whatever. And we're simply going to hope that it is going to work well going forward. So that is going to be the approach. Now, it sounds weird, and we'll get to just how weird it is. But I do want to point out it's not. I mean, that's exactly what we do on data fitting. Right? If you do data fitting and someone says, what are you doing? You'd say, well, I'm fitting a model. And you go, well, what do you really want to do? I wanted to be able to predict, starting next week, I wanted to be able to predict demand for my product. And they were like, well, how are you doing it? And you go, well, I'm using this data from last year. And they're like, yeah, but the demand last year is not the demand next year. And you go, yeah, I know. Anyway, so I'm just saying data fitting is very similar. And we'll get to what the essential assumption is something like that, yeah, but if the way demand varied last year is the same as how it continues to vary this year, then a model built on last year's demand data should be pretty good for next year, right? Or something like that, right? So it's the same thing in finance, maybe with more surprises, I would say. Okay, so we are going to get to portfolio optimization now. It is, in fact, a constrained least squares problem, at least in our formulation of it. So here's how we're going to do it. Remember, we have two desiderata. We want high return, which is the average of little r, and we want low risk, and the risk is the standard deviation. Variance, which is the square of that. Okay, so here's what we're going to do. What we're going to do is we are going to specify a required return rho. That's it. So if rho is 0.1, it means we are requiring a return of rho of 10%. That's it. Okay. Now, then what we're going to do is we're then going to minimize the variance of the time series little r. This is little r, which is the portfolio return. Now, the variance of something is basically that's not it's the variance is the mean square deviation from the mean. Okay, so normally, but the point is we're actually requiring the mean to be rho. So it's like, okay, so we just put that here. So the point is that the standard deviation of RW squared is, which is the mean square deviation from the mean. That's given by this expression here. Now, rho is given, R is data. And our job, of course, the variable that we're going to find out that we want to seek is W, the weight vector. The first constraint, which is linear, the linear constraint, equality constraint, says that W sums to 1. Well, that's kind of by definition, so that's fine. And the second one here is the one that says I want the average return, at least historically, to have been rho. So that's the idea. So let's see, let me talk about some of these things here. I think we've talked about most of these things. Here you can vary rho and you'll get different portfolios. And in fact, you can even think about what rho is. Rho tells you it's the required return, and the larger it gets, basically, people would say the more aggressive your portfolio is, because you're basically saying, if you say give me a portfolio that had 50% return, it'll do it. It'll do it by doing crazy stuff and shorting stuff and having high leverage, but it'll do it. Okay, so that's the idea. Okay, and so to be very precise about what we're doing when we solve this problem is we're really asking what would have been the best constant allocation had we known future returns. Now, that's a bit silly because, on its face, it's utterly useless because, if in fact, if I knew the returns over the next year, over the last year, and then went back in time, I wouldn't do this, that's for sure. If I knew the returns, I could actually make a bundle of money because I'd buy stuff that I know was going to go up and I'd short stuff that was going to go down and blah, blah, blah. So anyway, but that's what we're doing. To be very precise, we are finding a portfolio that would have worked last year. Roughly, right? Kind of weird, but that's what it is. Look, it's not any weirder than data fitting, frankly, because our job is to make something that works on data we've never seen. And to do that, we use data that we have seen, right? So, and then someone comes along and says, well, you have last year's data. You go, yeah, I'm using it to estimate, why? And they go, but you know why. Why do you need to estimate it, right? So you get the idea, but this is similar. Okay, now this is a constrained least squares problem, period, right? Because, I could put everything in the form with norm ax minus b squared subject to cx equals d. C has two rows. There are two linear equality constraints. That's the weight constraint and also the average return constraint. So we're going to write it this way. It is identical to what we had before. I did a few things like I dropped the 1 over t because if I change the objective by a factor, it doesn't change anything and it just lightens the notation. So there it is. Looks like that. And here, I should say what mu is. Mu is r transpose 1 divided by t. That is the vector of the mean returns of each of the n assets, right? So that's what that tells you what that is, right? Rho, again, is a parameter that we choose. Oh, and we're going to vary because when we vary it, we just get different portfolios with different levels of aggressiveness. And of course, that's an equality constrained least squares problem. And here's the solution. That's the KKT matrix. And this is the right-hand side here. So it's W, you get these two Lagrange multipliers. We actually don't care about them, but we are interested in W, right? This is an n+2 vector here. And so we simply solve this least squares problem, constrained least squares problem, any way we like. I'm for all I care, just make a, in your code, just make a backslash and you're done. Okay, so that's it. Oh, we could actually name a few things just to make this. I mean, in some cases we can do this. We can say what the solution is just analytically or by inspection. So here's an example. If I set rho equals rho risk-free, then what this says is, please go back last year and find me a portfolio of investments whose average return is the risk-free return. Oh, and also I'd like you to minimize the variance of the return. But you know what? The solution to that is just going to be this. It's going to be W equals EN. It's going to be put everything in the last asset, which is cash. Let me tell you why. Because if you use this, then the portfolio return is simply rho risk-free times ones. Oh, so cool. That's the average. We win, right? So we do that. Oh, also the variance is 0. It is, after all, risk-free, right? So that means it's just not, there's no risk. Oh yeah, and by the way, norm squareds don't come smaller than 0, so that is optimal for sure. So I'm just saying that that's an interesting point on that on this curve as we check. Now for other rows, that's not the solution. It's going to be something very different. But I just want to mention that that's an important special point where we can just tell you what the solution is. No KKT equations. But of course, if you were to assemble and solve the KKT equations with rho equals risk-free, that's a good homework problem, by the way. I hope you get back EN. That's, well, if you don't, your code is wrong. Okay. So these optimal portfolios, when you put them together, they perform significantly better than individual assets in terms of risk and return, right? So they'll have either lower risk for the same level of return or higher return for the same level of risk. They'll simply be better than the individual assets. Now, when you plot and you vary rho, remember rho is the thing that modulates. It's the parameter that modulates how aggressive our portfolio is. As we change rho, we get a portfolio, and it turns out it forms a straight line. And the reason is, if you look at this formula right here, you will see, if you look at this formula right here, you will see that W, well, I go back to this formula back here, and you say, how does this depend on rho? Well, look at this. The right-hand side has got rho in the first and the third block entry, right? So it turns out you can just check. I mean, well, matrix vector multiplication is linear or whatever, so it looks like this. It says that we can express it this way. Now, that's just a fixed portfolio. That's another fixed portfolio, and then you multiply by rho, which is kind of cool. So that's it. So what it says is that that the optimal portfolio, as a function of required return, is affine, and that's got a fancy name in finance. I don't know why they make it this complicated, but anyway, or it's not that impressive, frankly. But anyway, it's called the two-fund. They call it the two-fund theorem, and the reason is they're saying that every optimal portfolio is a combination of this fund, right, plus this one, and you're like, oh, times rho, and you're like, okay, whatever, fine, cool. But anyway, it's interesting. What it says though is that the risk-return curve is going to be on a straight line. Now, one end of the line, which is 0 risk, is simply the risk-free asset. Okay, so that's that. You'll hear this. Okay. So now we come, and I want to make it, I've hinted at it a couple of times, but I want to make it super explicit, right? That everything we're doing here rests on something which I call the big assumption. I don't know why I introduced the BA, but anyway, maybe it's because, who knows? We'll see how many times I use that acronym. But so here it is. The big assumption is basically future returns will look something like past ones. Now, when you take another course on statistics and things like that, then you can actually, you can say this more precisely if you'd like. You'd say something like, oh, the statistics of future returns, that come from this, look like the statistics of past ones or whatever. But the truth is, this is the assumption, essentially. I mean, it's vague. It's not a mathematical thing. I mean, what does it mean to say something looks like something? But that's the idea. Okay. Now, that is the implicit assumption. Now, by the way, every time you invest, you sign something somewhere, I promise you, that basically acknowledges that you understand that this is not the case. So they say things like, whatever, past performance is not a guarantee of future, blah, blah, blah. It's in some legalese, but every time you invest, or if you open a brokerage fund, something like that, somewhere you sign something that basically that makes you acknowledge that the big assumption is in play, and that's basically so you don't go back and sue them or something like that. Okay, all right, fine. Now it's often reasonably true, the big assumption, but actually there are times when it is shockingly not true, and people say they refer to these as a market shift or a change in regime or something like that. And in those cases, it's much less true. So just for example, in the last year, in the last 2 or 3 years, we've had stunning crashes of the market, followed by incredible periods of growth and more and just looking at those, your eyeball's going to remind you that this need not be true. However, if it, when it's true, while it's true, I should say, then it turns out a good weight vector for past realized returns should be good for future ones, right? And so here would be an example. You might choose W based on the last 2 years of returns and then use that weight vector for the next 6 months. So actually people do much more sophisticated things than that. And they might they might come up with a new W daily and stuff like that. But once you get the basic ideas that we're talking about, you would understand how to do that and why people do that. Okay, so that's the big assumption. And honestly, it's not it's actually not that much different from just data fitting, because that's, if you ask a statistician, what are you doing? I'm fitting a model. You go, how are you doing that? You go, well, I'm looking at all this past data. And I'm like, but you don't need to predict for past data if you know what the outcome was. And they go, yeah, but I want to use it for data I've never seen. And I'm like, well, why is it going to work? I mean, so basically they also have a big assumption, right? And their big assumption is buried in kind of mathematics and stuff like that, so you don't notice it. And basically it started on page 1, which was kind of like, well, I'll assume that these things are samples from some distribution, right? And that's their way to be very mathematically precise about saying that, well, I think the future data is going to look like the past data. So, okay, enough on that. Sorry, the only I'll say one last thing about that. The only thing I would say about that is this: it means don't take any of the models too seriously, right? So that would be kind of the takeaway message there. Okay, so let's look at an example. This is 20 assets. Actually, I think they're like ETFs or something. I can't remember what they are. Doesn't matter. There's 20 assets over 2,000 days. So that's 8 years or something like that. It's 200, roughly 8 years. And here's what you get. Here they are on a risk return plot. So here's the annualized return. Wow, some of these are like big earners, right? That's like a 18% return. Now their risk is pretty crazy too. It's like 30%. So and that makes sense. I mean, that means that these things, over a year, you shouldn't be surprised if they lose 10%, and you shouldn't be surprised if they return 40%, which is pretty high, right? So that's what that means. Let's see, what is that? I don't know what it is, but I can tell you from an investment point of view, that is a super bad news asset right there, because it is. Here's what it did. It over these 8 years. It generated a really nice, handsome loss, and it did so with extraordinary risk. So, okay, so that's pretty good. Oh, the Pareto optimal assets would be the ones here, right? Probably in this picture, it's just these three. Sorry, and it's that one. Okay, so Probably it's this one too. So those would be the Pareto optimal ones, meaning there is no single asset in this group that dominates it, and dominates means has higher risk and lower risk and higher return. So those are so there they are. It's roughly like that. Let's see what these optimal portfolios look like. Well, there it is. Okay. So this line shows you what the optimal portfolio, what their risk and return is. Now this is as we tune the knob rho, right? So if I set, in fact, rho is literally this number right down. Oh, no, sorry, my mistake. That's rho right there. Okay, so when we say I want an annualized return of 0.4, or I want an annualized return of 10% or 20%, that's right over here. Okay, and this is, as I said, it's a line, and when you fiddle with rho, you get that line. Okay, okay. So, and over here, plotted in dark, as you see one of the dark circles, that's the 1/n portfolio. Actually, it's not so bad, right? It's kind of in the middle, gives you a 10% return and a 23% annualized risk. So, okay, and okay. Oh, people would explain that by saying that you have, you've diversified, and that you had your 20 assets, and in each period, some went up, some went down, and the result was the 1/n portfolio didn't go up and down as much, or something like that. Okay. So we're going to look at 5 portfolios. In fact, they're marked here. We're going to ask for 10%, 20%. That's this 10%, 20%, and 40%. That's extremely aggressive. And we'll also look at 1/n here. So here they are. And the risk-free. That's simple. So let's take a look at them, and we'll look at train and test. So the way this training was done on a period of 8 years, and that was how we got the capital R matrix. That's where all the data came from. And out of that past data went into our sausage making machine, which is linearly constrained least squares, and out came W. Okay, so that's what that is. Now let's look at some of the portfolios. Here's one. I guess the risk-free return is 1% per year. Okay, so here, all of these, the train will be exactly the required number, because that's an equality constraint in the in our problem formulation, right? When we say rho is 0.5, 0.4, we mean you have to do that. So these are exactly these numbers. Okay, now the test is a different thing. The return, and that's tested on another period of about 2 years. That's a 500-day period, but let's just look at them. So here the risk-free, by the way, continues at 1%, right? The rho equals 10%. It says on the test thing we get 8. That would be just fine. I mean, that makes perfect sense, right? Because someone said, "Hey, I thought you asked for 10%." And you go, "No, let me be precise. I constructed a portfolio that on the past 8 years would have made 10% exactly." And you'd say, why would we believe that on these 2 years it would make 10? But 8% is close enough to 10 that we'd say that's cool. And you can sort of look at these, and some of these kind of make sense, right? So you can see that on the test thing they made different. One big difference: the uniform weights, or 1/n portfolio, actually, for whatever reason, did 10% on those 8 years, and then 21% on the test. Well, this has to do with these so-called regimes, right, where, roughly speaking, things change. Okay, let's look at the risk. So the risk is, of course, for risk-free, it's 0 on train and test. Oh, and the leverage is 1. Of course, it's 1. It's very long. This is very safe. It's long only. If we ask for 10%, this is sort of interesting. The risk we get in train is 0.09, okay, 9%. Now on the test set you get 7%, so that's actually in your favor. I mean, it's like okay, but I mean this happens. This is fine, right? So it means that it was less. You had less risk on that 2-year period than the 8-year period on the basis of which is how we chose W. And if you look up here, for rho equals 20%, you would get a risk. you made a risk you got a return of 20%. On test it was 15. The risk you got was about 0.18, and then on the test it was somehow the test period is clearly a little bit more benign or something like that, and your risk, but it's in the ballpark and you'd expect this. So these are all the kind of things you would sort of you'd sort of guess would happen, right? So this just shows you how you do this. Let's take a look at the portfolio value of these 5 portfolios. Oh, and please note the plot, right? So 2000, this is about 8 years here. It's 8 years, right? So, and we start with, 10,000, that's the traditional number. And, look, I mean, this is crazy. How, the black one is insane. That's when we're super risky, and we've got. I should go back and say something about the leverage. The leverage is like 5.48. So that means it means that for basically like every dollar of value in your portfolio, your absolute value position is like 5.48. It's a fair amount of leverage. There's places that operate with higher leverage than that. Usually, I might add, with other people's money. That's the best way to run a leveraged portfolio, is have other people's money. Oh, and make sure you have a passport to a country with no extradition treaty with the U.S. That would be the other 2 tips. Well, okay, I digress. Let's go back to this. Okay, so this is kind of extraordinary, right? Like even 50 would have been pretty good. That's a 5x return over this 8-year period. And you can see that this the green one, that's one where we asked for 20%, kind of gets there. Let's see. Oh, you can barely see the blue one going up because the risk-free rate I think we set was 1%. And then you can see several other things. For example, the 10% value one, when we ask for 10%, you can see that it goes up and does pretty well. 10% per year times 8 years, it's maybe going to double in size or something, roughly, right? And that's about what it is, maybe less than that. But okay. And then here's the 1/n portfolio. That's the red. Actually, what's kind of cool is somewhere in the range of day 1200 to 1300 or something. It's been, I don't know, was that 3 years? It's been 4 years. It's been 4 years, 5 years, right around 5 years. Someone says, hey, how's your 1/n portfolio doing? And the answer is, you've actually lost money compared to where you started 4 years ago. Okay, none of the others do that. And then here it is on test. So the test is running over 500 days. This is this crazy, insane, super aggressive thing. And sure enough, here's the test. It starts up you start at 10,000. You go down to, I don't know, that's pushing on 11. So you drop value by 10%. That's called a drawdown. That's a good slang term to know. So your portfolio immediately went down 10%, then it shot up, down, up, down, up, down, this kind of thing. So, and that's actually that's what risk means, is the portfolio value is going shooting up and down and stuff like that. So, by the way, if you have a stomach for this kind of roller coaster ride, then fine. And you can look at the others, and they do just what you think they would do. Oh, I should say, I should admit, the 1/n thing ends up doing pretty well, I guess. I mean, it's got pretty high risk, but it does pretty well. Okay, so this is sort of an introduction to this topic. You can take an entire class on nothing but this. You can take multiple classes on other aspects of finance. I should also mention a couple of things. It's easy to think of general, things you would do next. For example, people update the weights every single day, sometimes by just solving another problem like this. Another thing not that's out of the scope of this class is you can add constraints on the weights. And later, maybe, you'll take a class on convex optimization, and you'll see how linearly constrained least squares can be extended to include inequality constraints. So that's also something that you'd see in later. Well, you see a lot of stuff later. Maybe the principal thing you'd see later is that people who do this think entirely in terms of statistics. So my friends who do finance can't even believe that here I am explaining a little bit about portfolio optimization with no statistics. And you will notice we didn't have any statistics. However, it's very, very close. Once you learn the statistics and stuff like that, it'd be the same things, the same formulas. It's identical. The only difference is that they're giving an interpretation statistically. Okay, so that's our first application of constrained least squares.